What is Python? Python is a high-level, interpreted programming language designed for readability and simplicity. Its syntax is clean and emphasizes code readability, which allows developers to express concepts in fewer lines of code compared to other languages. Python supports multiple programming paradigms, including procedural, object-oriented, and functional programming. This line of code is a classic example of a starting program in many languages. In Python, the print function is used to output data to the standard output. In this case, the string "Hello World" is displayed to the screen. This simple command demonstrates Python's straightforward syntax and ease of use for basic tasks. History of Python. The history of Python is an interesting journey that takes us back to the late 1980s. The language was created by Guido van Rossum and was officially released in 1991. Python has since become one of the most popular programming languages in the world. Python was conceived in the late 1980s by Guido van Rossum at Centrum Wiskunde en Informatica, CWI, in the Netherlands as a successor to the ABC language, itself influenced by CTL, capable of exception handling and interfacing with the Amoeba operating system. Its implementation began in December 1989. Van Rossum shouldered sole responsibility for the project as the Benevolent Dictator for Life, BDFL, until he stepped down from the role in July 2018. Python 2.0 was released in 2000, introducing new features like list comprehensions and a garbage collection system. Python 3.0, released in 2008, was a major revision that was not completely backward compatible. However, it laid the foundation for modern Python programming. Features of Python. Python is known for its simple syntax and readability, making it an excellent choice for beginners and experienced developers alike. Here we'll highlight key features of Python which contribute to its popularity and widespread use. The line of code demonstrates Python's simplicity and readability. The print function outputs the string "Hello Python" to the console, illustrating Python's ease of use for basic tasks. No complex syntax is needed to perform simple operations, making the learning curve more manageable. This ease of use is one of Python's standout features, alongside others such as dynamic typing, extensive libraries, object orientation, expressive syntax, and it being interpreted rather than compiled, which aids in rapid development and debugging. Applications of Python. Python is used in various domains and for numerous applications due to its simplicity, readability, and vast ecosystem of libraries. Here's an example showing a simple Python script used for web scraping, which is one of its applications. This code snippet demonstrates how Python can be used for web scraping. It imports requests for making HTTP requests and beautiful soup from BS4 for parsing HTML. It fetches the content of http:/example.com and prints the title of the web page. Installing Python. Before writing your first Python program, you need to install Python on your machine. Python can be installed from the official Python website or through package managers on various operating systems. To install Python, visit the official Python website at python.org and download the installer for your operating system, Windows, macOS, or Linux. Run the installer, follow the prompts, and ensure that you check the box to Add Python to Path if you're on Windows. After the installation is complete, you can verify the installation by opening a terminal or command prompt on Windows and typing python-version, which should display the installed Python version. Running Python code. To run Python code, you need a Python interpreter. You can execute it interactively in a shell or write your scripts in files, usually with a .py extension, and run them. The provided code is a simple Python statement that outputs the text "Hello World" to the console. When this line of code is executed, it calls the print function, which prints the string in the parentheses to the standard output, typically the screen. Python 2 versus Python 3. Understanding the differences between Python 2 and Python 3 is crucial for beginners because it determines which version of Python they should learn and use for their projects. Python 3 is the present and future of the language. However, some legacy code is still maintained in Python 2. In this code, we see the difference in syntax for printing a statement to the console. In Python 2, print is a statement and does not require parentheses. In Python 3, print is a function and requires parentheses. Running the Python 2 line in a Python 3 interpreter will result in a syntax error. This change is one of the simplest, but also one of the many syntactical differences between the two versions. Syntax and indentation. In Python, syntax refers to the set of rules that defines the combinations of symbols that are considered to be correctly structured programs. Indentation, on the other hand, is unique to Python, and it is used to define the blocks of code. Correct indentation is critical because Python uses indentation to define the scope of loops, functions, classes, and other structures. In this code snippet, the if statement checks if the condition true is satisfied. Since true is always true, the indented block under the if statement will execute. Notice that the print function is indented with 4 spaces to indicate that it is part of the if block. If this indentation is not consistent, Python will raise an indentation error. Comments and docstrings. In Python, comments are used to annotate code to make it easier to understand. They are ignored by the Python interpreter. Docstrings, documentation strings, serve a similar purpose, but are associated with modules, functions, classes, or methods, and can be accessed at runtime. The code starts with a single-line comment, followed by a multi-line docstring. Then a function named sample function is defined with its own docstring inside. An inline comment appears within the function. Comments and docstrings are essential for providing explanations and information about the code that do not affect its execution. Variables and data types. In Python, a variable is a name assigned to a memory location where a value is stored. Variables are created when you first assign a value to them. You don't need to declare the type of the variable, as Python is dynamically typed, which means the type is inferred at runtime. In this piece of code, x is a variable that holds the integer value 5, and y is a variable that holds the string hello world. Python understands the type of x to be an integer and y to be a string, based on the values assigned to them. Type conversion. Type conversion in Python, also known as typecasting, is the process of converting the value of one data type, integer, string, float, etc., to another. This is often necessary when you need to perform operations that require a specific data type. Python provides several built-in functions for explicit type conversion, including int, float, and star. In this code snippet, we're converting different data types using Python's built-in functions. First, we convert an integer to a float using float, which changes 5 to 5.0. Next, we convert the string 10 to an integer using int, which allows us to perform arithmetic operations. Lastly, we change a float 20.0 to a string using star, so we can concatenate it with other strings or use it in a context where a string is required. Basic operators. In Python, arithmetic operators are used to perform mathematical operations like addition, subtraction, multiplication, and division. The plus operator adds 2 operands. The minus operator subtracts the second operand from the first. The SOR operator multiplies both operands. The slash operator divides the first operand by the second. Input and output. In many programs, you'll want to collect input from the user. Python provides a simple way to do this using the input function. This function pauses program execution and waits for the user to enter some text. The code uses input to prompt the user for their name and stores the result in a variable called user_input. It then prints a greeting that includes the user's name by concatenating it with the greeting string. String formatting. String formatting in Python is a technique used to create strings that have variable content. Instead of concatenating strings together to build a message, string formatting provides a more readable and convenient way to include variables within strings. There are several string formatting methods, including the old-style cent operator, the newer .format method, and f-strings introduced in Python 3.6. In the code example, we use an f-string, which is a string prefixed with the letter f before the opening quote. Within this string, you can include expressions inside curly braces that will be evaluated at runtime and formatted using the surrounding context. The variable name gets replaced with John, and the variable age gets replaced with 30. When the welcome message is printed, it outputs, "Hello John, you are 30 years old." Conditional statements. if-else, elif. Conditional statements in Python allow the program flow to change based on whether certain conditions are met. They are written with the if, elif, and else keywords. The code defines a variable x with the value 20. It first checks if x is less than 10 using an if statement. If this condition is false, it proceeds to the elif, which means else if, to check if x is less than 20. If both conditions are false, the else clause is executed, printing that x is 20 or more. Since x is 20, the else clause is the one that is executed in this example. Logical operators. Logical operators in Python are used to combine conditional statements. They include and, or, and not, which return true or false depending on the conditions they are evaluating. The and operator returns true if both conditions are true, or returns true if at least one condition is true, and not inverts the Boolean value of the condition that follows it. In the provided code, we start by assigning 25 to x and 75 to y. We then check whether both x is less than 50 and y is less than 100, which is true, as both conditions are met. The second print statement checks if either x is less than 50 or y is greater than 100. Since x is indeed less than 50, the result is true, even though y is not greater than 100. The last print statement uses not to invert the result of x and 50. Since x is less than 50, x less than 50 is true, hence not x 50 returns false. Loops for while. The for loop is used to iterate over a sequence, such as a list, tuple, string, or range. The loop starts with for, followed by a variable name that takes on the value of each element in the sequence for each iteration. Range 5 generates a sequence of numbers from 0 to 4. The loop body, indented by 4 spaces, executes the print I statement 5 times, each time with I taking on the next value in the range. Break and continue statements. In Python, break and continue are two control flow statements that can alter the flow of a loop, for or while. The break statement is used to exit the loop immediately, regardless of the iteration number. The continue statement skips the rest of the loop for the current iteration and moves on to the next iteration. In this code, we have a for loop that iterates over a range of numbers from 0 to 9. The if I equals 5 condition checks if the loop variable I is equal to 5. When it is, the break statement is executed, which terminates the loop immediately. The if I sent 2 equals 0 condition checks if I is an even number. If true, the continue statement is executed, which skips the current loop iteration and prevents the execution of print I for even numbers. Hence, this loop will only print odd numbers less than 5. Loop else clause. Python offers an additional clause with loops called else. It can be used with both for and while loops. The else clause is executed after the loop finishes its execution, as long as it was not terminated by a break statement. This can be helpful for scenarios where you want to take a certain action after a loop concludes naturally, and a different action if you exit the loop early. In the given code, the for loop iterates over a range from 0 to 4. The print I statement outputs each number. After finishing all iterations, since there is no break statement to exit the loop early, the else clause is executed, and loop completed normally is printed. If a break was present inside the loop and executed, the else clause would be skipped. Pass statement. The pass statement in Python is a null statement. It does nothing when executed. It's used as a placeholder in a block where a statement is syntactically required, but you don't want to execute any code. In this code snippet, we have a for loop iterating over a range of 5 numbers, 0 to 4. The if statement checks if the current number is 3. When the number is 3, the pass statement is executed, which does nothing, thus effectively skipping any action for that iteration. For all other numbers, the else block executes and prints the number. Hence, the output will be 0, 1, 2, 4, since pass did nothing when the number was 3. List. In Python, a list is a mutable, ordered collection of items. Lists can contain items of different types, including other lists. They are defined by enclosing their elements in square brackets. Below, we'll create a simple list and perform some basic operations. In this example, we created a list named myList, containing integers from 1 to 5. We then use the append method to add the integer 6 to the end of the list. The len function is then used to find the number of items in the list. We also demonstrate how to remove an item from a list using the remove method, which in this case removes the first occurrence of the value 3. Tuple. A tuple in Python is a collection which is ordered and immutable, meaning that once a tuple is created, its contents cannot be changed. Tuples are often used for data that shouldn't be altered, like dates or user details. Tuples are defined by enclosing the elements in parentheses. In the code provided, we first define a tuple named example tuple with 3 elements, an integer 1, a string apple, and a floating point number 3.14. Then, we print the whole tuple, which will output 1 apple 3.14. Next, we demonstrate accessing individual elements of a tuple using index notation, as with example tuple 1, which will access the second element. Indexing starts at 0 and output apple. Set. In Python, a set is a collection which is unordered, unindexed, and contains no duplicate elements. Sets are mutable and can be used to perform mathematical set operations like union, intersection, difference, and symmetric difference. They are defined by values separated by commas inside curly braces. The code first creates a set with elements 1, 2, 3, and 4. Note that 3 and 2 appear twice. However, in the resulting set, they only appear once because sets eliminate duplicates. The add method is then used to add the element 5 to the set. Afterwards, the remove method is called to eliminate the element 2 from the set. Throughout, the set maintains uniqueness of elements, but does not preserve order of insertion. Dictionary. In Python, a dictionary is a collection of key-value pairs where each key is associated with a value. Dictionaries are unordered, changeable, and do not allow duplicates. They are very useful for storing data values like a map, which unlike other data structures that hold only a single value as an element. The code first creates a dictionary with 3 key-value pairs: name associated with Alice, age with 25, and email with alice@example.com. It then prints the value associated with the key name using square bracket notation. The value for the key age is retrieved using the get method, providing a way to safely access keys. Following this, the value associated with email is updated to alice@sample.com. The final print statement outputs the entire dictionary with the updated email address. Common operations. In Python, common data structures like lists, dictionaries, sets, and tuples come with a variety of operations that can be performed on them. These operations include adding, removing, or modifying elements, as well as querying information about the stored data. Understanding these operations is essential for manipulating data stored in these structures. The code block illustrates some basic operations on different data structures. 1. Lists append adds an element to the end of the list, and remove removes the first occurrence of the specified value. 2. Dictionaries get retrieves the value for a given key, and assigning a value to a new key adds a new key-value pair. 3. Sets add inserts a new element into the set, and discard removes an element if it is a member. 4. Tuples are immutable, so you can't add or remove elements. Indexing is used to access elements, and count returns the number of occurrences of a value. List comprehensions. List comprehensions provide a concise way to create lists. It consists of brackets containing an expression followed by a for clause, then 0 or more for or if clauses. The expressions can be anything, meaning you can put in all kinds of objects in lists. In this example, we create a list of numbers from 0 to 4 using a list comprehension. The x for x in range 5 within the brackets is the list comprehension part, which executes the expression x for every x in the sequence created by range 5. Iterables and iterators. In Python, an iterable is an object that can be looped over, meaning it can return its elements one at a time. Common examples include lists, tuples, dictionaries, and sets. An iterator is an object that represents a stream of data. It's what actually does the work of producing values from an iterable when you loop over it. The iterator is created by calling the iterable's iter method, or the built-in iter function. Each time you want a new value from the iterator, you call its next method, or the next function. In the provided code, MyList is an iterable, a list. IterObj is the iterator obtained from MyList. The next function is called on iterObj to get the values from the iterator one by one. When next iterObj is first called, it returns 1, which is the first value in MyList. The next two calls to next iterObj return 2 and 3, respectively. After the third value, a subsequent call to next would raise a stop iteration exception, indicating there are no more values to iterate over. Defining functions. In Python, a function is a block of organized, reusable code that is used to perform a single, related action. Functions provide better modularity for your application and a high degree of code reusing. In the code example, we define a function named greet that takes one parameter, name. The function uses this parameter to create a greeting string and returns it. The def keyword is used to start the function definition, followed by the function name and parentheses with any parameters inside. The body of the function is indented, which is crucial in Python as it defines the scope of the function. Arguments and parameters. In Python, functions can take inputs to perform tasks. These inputs are known as parameters and arguments. A parameter is a variable listed inside the parentheses in the function definition. An argument is the value that is sent to the function when it is called. In the code, name is a parameter of the function greet. When we call greet with the string Alice, Alice is the argument. The function prints a personalized greeting using the argument passed to it. Return statement. In Python, the return statement is used within a function to send a function's result back to the caller. It terminates the function and optionally passes back an expression to the caller. The function addNumbers takes two arguments, a and b, and calculates their sum. The return statement is used to provide the sum back to the function caller. When addNumbers 5,3 is called, it returns 8, which is then stored in the variable total and printed out. Docstrings. Docstrings, or documentation strings, are literal strings used to document a specific segment of code. Unlike regular comments, they are retained throughout the runtime of the program. This allows the programmer to inspect these comments at runtime. Docstrings are written within triple quotes and are placed immediately following the function header. In the provided code, the function greet takes a parameter name. The docstring immediately following the function definition provides a description of what the function does. To retrieve the contents of the docstring, you can access the function's doc attribute, e.g. greet.doc. When programming in Python, it's good practice to write docstrings for public functions. This improves code readability and helps with auto-generation of documentation. Default argument values. Default argument values allow functions in Python to have optional parameters. This means that you can specify a default value for one or more arguments. This can be useful when you want to provide a common default for an operation, but also offer the flexibility for the user to provide their own value. In the provided function greet, the parameter name is required, no default value is provided, while message has a default value of hello. When the function is called with both arguments, it will use the supplied message. However, when called with only the name argument, it will use the default hello as the message. The result of the first call, greet Alice, good morning, will be good morning, Alice, and the result of the second call, greet Bob, will be hello, Bob. This demonstrates the use of default argument values in Python functions. Keyword and positional arguments. In Python, functions can accept arguments by position or by keyword. Positional arguments are matched in order based on the position in which they are provided. Keyword arguments are passed by explicitly specifying the parameter name and value during the function call, allowing them to be passed in any order without following the defined sequence in the function declaration. In the provided code, we define a function greet that takes two parameters, first name and last name. First, we call greet using positional arguments by passing Jane and Doe in the exact order as the parameters are defined. In the subsequent call, we use keyword arguments by including the parameter names directly, allowing us to swap the order without affecting the output. Keyword arguments add clarity to the function call and can be especially useful when a function has many parameters or when defaults are involved. Variable length arguments, args and kquargs. In Python, sometimes we need a function that can accept more arguments than we specified while defining it. This can be achieved by using variable length arguments. The args will enable you to pass an arbitrary number of positional arguments, and kquargs will allow you to pass an arbitrary number of keyword arguments. The my function is defined with args and kquargs to accept any number of positional and keyword arguments respectively. When we call my function with 3 positional arguments, 1, 2, 3, and 2 keyword arguments, name equals Alice, age equals 25, it prints tuples of positional arguments and dictionaries of keyword arguments. Anonymous functions, lambda. In Python, anonymous functions, known as lambda functions, are small one-liner functions that are defined without a name. They are created using the lambda keyword, which is why they are also referred to as lambda functions. They can take any number of arguments, but can only have one expression. They are often used for short-duration tasks, where defining a formal named function is not necessary. The code defines an anonymous function that calculates the square of a number x. The lambda keyword creates the function with x as its input argument. After the colon, the expression x*x defines what the lambda function returns. The function is assigned to the variable square. When square 5 is called, the lambda function computes 5*5, resulting in 25, which is then printed out. Nested functions. In Python, functions can be defined inside other functions. These are known as nested functions. The inner function is only accessible within the outer function, meaning it can be called only within the scope of the outer function. In the provided code, outer function takes a parameter text. Within this outer function, a nested inner function is defined and called. The inner function prints the parameter text, accessing it from the outer function's scope. When outer function is called with the argument hello from the inner function is executed and prints the provided text. This demonstrates how nested functions can access variables from their enclosing scope. Function decorators. Function decorators in Python are a powerful and advanced feature that allow modification of functions using other functions. They decorate another function by extending its behavior without permanently modifying it. In the provided code, myDecorator is a decorator function which takes another function func as an argument. Inside myDecorator, there is another function defined called wrapper, which enhances the behavior of func by executing additional code before and after func is called. The @myDecorator syntax is used to apply this decorator to sayHello function. When sayHello is called, instead of just printing hello, it executes the additional code specified in the wrapper, essentially extending sayHello's behavior without modifying its implementation. Importing modules. In Python, modules are simply files with the .py extension containing Python definitions and statements. To use the functionality provided by a module, you have to import it using the import statement. In this code, we use the import statement to import the math module, which contains various mathematical functions. After importing it, we can access the functions inside it using the dot notation. Here, we call the squart function to calculate the square root of 16 and print the result. Creating modules. In Python, a module is a file containing Python definitions and statements. Creating a module can organize your code, make it reusable, and help you break down complex problems into simpler chunks. Here, we have created a simple module with a Python file that contains a function, myFunction, and a variable. To use this module in other Python scripts, save it as mymodule.py and import it using the import statement, import mymodule. You can then access the function and variable using dot notation, mymodule.myfunction, mymodule.variable. Using imported functions and attributes. Once a module or package is imported into a Python script, you can use its functions and attributes. For example, if you import the math module, you have access to various mathematical functions and constants, like sqr for square roots and pi for the mathematical constant pi. In this code, we're importing the entire math module, which provides a collection of mathematical functions and constants. Using the math module's squart function, we calculate the square root of 16. The value of math.py gives us the constant pi. Both the function and the constant are accessed with the dot notation, prefixed by math, the name of the module. Standard modules, math, datetime, etc. The math module provides access to the mathematical functions defined by the C standard. This code imports the math module, uses suart to calculate the square root of 16, accesses the mathematical constant pi, and calculates the sine of 90 degrees after converting degrees to radians using math.radians. The dir function. The built-in dir function is used to list the names in the current scope. When called without arguments, it returns the list of names in the current local scope. When called with an argument, it attempts to return a list of valid attributes for that object. In this code snippet, we first import the math module, which contains mathematical functions and variables. Then we called math, which returns a list of all the attributes, functions, variables, etc. defined in the math module. This can be particularly useful when exploring modules and understanding what functionalities they provide, or when you want to list all the members of a module. Packages and subpackages. A package in Python is a directory that holds a collection of modules and can include subpackages. Packages allow for a hierarchical structuring of the module namespace and are a way to organize related modules. A subpackage is a package that is a subdirectory of a larger package. In the provided structure, my package is a package containing two subpackages, subpackage 1 and subpackage 2. Each subpackage has its own init.py file, which may be empty or initialize the subpackage. The file structure allows for modules within subpackages to be imported and used. In the code example, module 1 is imported from subpackage 1, and then a function, myFunction, from module 1 is called. This demonstrates how to access functionality within a hierarchical package structure. Installing third-party packages with pip. Pip is a package installer for Python. It allows you to install and manage additional packages that are not part of the Python standard library. This is very useful when you need a module that offers extra functionality. To use pip, you need to have it installed, though it comes bundled with Python versions 3.4 and above. For earlier versions, you might need to install it manually. This command installs a package named packagename. Pip reaches out to the Python package index, PyPI, to get the package's files and dependencies. Once the command is executed, pip downloads and installs the package for your Python environment. You only need to replace package name with the actual name of the package you want to install. For example, to install the popular requests library, you would run pip install requests. Working with files. In Python, before we can read from or write to a file, we must open it using the open function. This function creates a file object, which serves as the connection between our code and the file itself. The code illustrates opening a file named example.txt in read mode, R. The open function returns a file object stored in the variable file. After performing file operations, the file.close method is called to close the file and free up any system resources. Reading from a file. Reading from a file is one of the most common file operations in Python. You open a file to read its contents and process the data. The code uses the with statement to open a file called example.txt in read mode, R. This is the recommended way to open files because it ensures that the file is properly closed after its sweep finishes, even if an error occurs. The open function returns a file object, which is then stored in the variable file. The read method is called on the file object to read the entire contents of the file into the variable content. Finally, the print function is used to output the contents of content to the console. Writing to a file. Writing data to a file is a common task in programming. In Python, this can be done using the open function with the mode W for overwriting an existing file, or A for appending to an existing file. In the given code, we use Python's with statement to open a file named example.txt in write mode. The with statement ensures that the file is properly closed after its sweep finishes, even if an error occurs. The file.write function is then used to add the text hello world to the file. If example.txt exists, it will be overwritten. If it does not exist, it will be created. With statement, context managers. The with statement in Python simplifies exception handling by encapsulating common preparation and cleanup tasks in so-called context managers. For example, when dealing with file operations, the with statement ensures that the file is properly closed after its suite finishes, even if an exception is raised. This makes the code more concise and readable. In this code, openExample.txt R is a context manager that manages the file named example.txt. The with statement takes care of opening the file, and as soon as the block of code within the with statement is executed, it closes the file automatically. The alias file is used to perform operations on the file inside the block. File.read reads the file content, and print content displays it. The file is closed when the block is exited, even if exceptions occur. Manipulating paths with os.path. The os.path module in Python provides a way of using operating system-dependent functionality to manipulate file paths. This is useful for reading, writing, and organizing files on your file system. This code demonstrates how to use various functions from the os.path module to manipulate file paths. First, we import the os module. Then we obtain the current working directory using os.getCE. We join directory names to get a full file path using os.path.join. os.path.split then helps us to separate the file path into the directory path and file name. Lastly, os.path.exists is for checking whether the joined path actually points to an existing file or directory in the file system. File and directory operations with os. One common file operation is checking whether a file or directory exists. We can do this using the os.path.exists function. The code imports the os module, defines a file path, and then uses os.path.exists to check if the path exists. If the path exists, it prints a confirmation message. Otherwise, it prints that the file does not exist. Handling file exceptions. When working with files in Python, it is important to handle exceptions that may occur during file operations to prevent the program from crashing and to provide informative error messages to users. One common exception to handle is the file not found error, which occurs when the file you're trying to access does not exist. Using a try except block is the standard way to catch and handle exceptions. In this code snippet, we use a try except block to handle a possible file not found error. We attempt to open and read the content of example.txt using a with statement, which ensures that the file is properly closed after its suite finishes, even if an exception is raised. If example.txt does not exist, the code in the except block is executed, informing the user that the file could not be found, rather than crashing the program. Syntax errors versus exceptions. Syntax errors, also known as parsing errors, are the most basic type of error. They arise when the Python parser is unable to understand a line of code. Syntax errors are usually due to not following the proper structure, syntax of the language. In the code provided, there is a syntax error because the print statement is missing its closing parentheses. This is an example of a typical syntax mistake where the Python interpreter cannot parse the line as it does not conform to the language syntax rules. Try except blocks. In Python, errors that occur at runtime are called exceptions. They disrupt the normal flow of a program. To handle these exceptions, Python provides try and except blocks. The code that could potentially cause an exception is put in the try block, and the code to execute if an exception occurs is put in the except block. The code first tries to convert a user input to an integer and then performs a division operation. If the user inputs 0, a 0 division error occurs, and the program prints, "You cannot divide by 0. If the user inputs something that can't be converted to an integer, a value error occurs, and "Please enter a valid number" is printed. If there are no exceptions, the division result is printed. Multiple except clauses. In Python, you can use multiple except clauses to handle different types of exceptions that may arise in a try block. This allows specific responses to each exception type. The else clause. In Python, the else clause is used in try except blocks. It defines a block of code to be executed if no exceptions are raised in the try block. The code starts with a try block that attempts to read an integer from the user and divide 100 by that number. If the user enters 0, a 0 division error is raised and caught by the except block, which prints an error message. If no exception is raised, the else block executes and prints the result of the division. The else block only runs if the try block does not raise an exception. The finally clause. In Python, the finally clause is an optional clause of the try statement. It is intended to define cleanup actions that must be executed under all circumstances. A finally clause is always executed before leaving the try statement, whether an exception has occurred or not. In the provided code block, we start by trying to convert an input into an integer and then attempt a division operation. 3 scenarios may unfold here. 1. The user inputs a valid number other than 0, and the division goes smoothly. The finally block executes after the try block. 2. The user inputs something that's not a number, raising a value error, which is handled by the corresponding except block. The finally block executes afterwards. 3. The user inputs 0, raising a 0 division error, which is handled by its corresponding except block. The finally block executes following this. Regardless of the outcome, the finally block will run, making it a solid place for cleanup code, like closing files or releasing resources. Creating custom exceptions. In Python, you can define your own exceptions by creating a new class. This new exception class has to be derived from the built-in exception class or one of its subclasses. Custom exceptions are useful when you want to raise an error specific to your application's domain. The code defines a custom exception called myCustomError, which inherits from the base exception class. The yorinit method is overridden to accept a custom message, which defaults to something went wrong in my application, if none is provided. The super doc_init self.message call ensures the message is properly initialized in the base exception class. The usage example demonstrates raising the custom exception with a specific message, which is then caught in an except block and printed out. Assertions. Assertions in Python are a debugging aid that tests a condition. They are not intended to handle runtime errors, but to help developers identify bugs more quickly. An assertion is followed by a condition. If the condition is true, the program continues to run. If it's false, the program stops and throws an assertion error. They are best used when you want to halt the program immediately if a certain condition is not met, and are mainly used for sanity checking. In the given code, the assert statement is used to verify that the variable x is less than 100. If x is 99 or less, the assertion passes and the program continues. If x is 100 or more, an assertion error with the message x should be less than 100 is raised, interrupting the program flow. Thus, assertions act as internal self-checks for your program. Classes and objects. In Python, classes are blueprints for creating objects. Objects are instances of classes and encapsulate data with code to work on that data. Classes can have methods, functions, and attributes, and objects created from a class can use these methods and attributes. The code defines a dog class with an initialization method, goinit, which is called when a new object is created from the class, setting the name and breed of the dog. The bark method makes the dog object speak. An object mydog is created from the dog class with Fido as its name and Labrador as its breed. When mydog.bark is invoked, it outputs Fido says woof. Defining classes. Classes provide a means of bundling data and functionality together. Creating a new class creates a new type of object, allowing new instances of that type to be made. The dog class is defined with an init method, which is the class constructor. It initializes the object with name and age attributes. Bark is a method defined to print a message. An object D is created from the dog class, and then its bark method is called. Instance methods. Instance methods are functions defined inside a class and can only be called on an instance of that class. They operate on the attributes of specific instances of the class. The dog class has an instance method speak, which uses the self keyword to access the name attribute of the instance it's called on. Thus, when we create two instances of dog, dog1 and dog2, with different names, and call their speak methods, each one returns a string unique to the instance, showing this instance method acts on the data tied to the specific object. Constructor, init method. In Python, a constructor is a special method of a class which gets called when a new instance of the class is created. The purpose of a constructor is to initialize the instance's attributes with specific values. The for init method is the constructor method in Python and is involuntarily invoked during the creation of an object. In the provided code, the car class has a nor_init method that takes 4 parameters: self, brand, model, and year. The self parameter refers to the instance being created, while the other 3 parameters are values that are passed to the constructor to initialize the instance's attributes. The self.brand, self.model, and self.year are instance attributes that hold the value specific to each car object created. When my car is created by calling car, Toyota, Corolla, 2020, the score_init method is called, setting the brand to Toyota, the model to Corolla, and the year to 2020 for this specific instance. Instance variables and class variables. In Python, class variables are shared across all instances of a class. They are defined within the class but outside any instance methods. Instance variables, on the other hand, are variables that belong to an instance of a class. Each instance has its own copy of these variables. In the given code, species is a class variable of dog, shared by all instances. Name and age are instance variables, unique to each dog instance. Accessing species uses the class name, while accessing name and age uses the instance name. Inheritance. Inheritance in OOP allows a class to inherit attributes and methods from another class, enabling code reusability and the creation of hierarchical class structures. The class that inherits is called the child or subclass, while the class being inherited from is the parent or superclass. In the provided code, animal is a superclass that defines the structure and behaviors common to all animals. The speak method is meant to be overridden by subclasses because it's a behavior that varies among animals. Dog and cat are subclasses inheriting from animal, and they provide their own implementation of the speak method. Instances of dog and cat can use the speak method, demonstrating that they have inherited this method from animal. By calling the speak method on Fido and Whiskers, we get woof and meow, respectively, displaying polymorphism through inheritance. Polymorphism. Polymorphism is a concept in OOP that allows objects to be treated as instances of their parent class, rather than their actual class. The literal meaning of polymorphism is many shapes. It means that the same interface or method exists in different forms. In Python, polymorphism allows us to define methods in the child class with the same name as defined in their parent class. This code demonstrates polymorphism in Python. First, it defines a base class bird with a method sing. 2 subclasses sparrow and parrot inherit from bird and override the sing method. The function birdsong takes any kind of bird and calls its sing method. Despite the objects being instances of their respective classes, sparrow, parrot, or bird, when we pass them to the birdsong function, it calls the appropriate sing method defined in each class. This showcases that the same operation may behave differently on different classes, which is polymorphism. When birdsong is called with each type of bird, the output reflects their individual sing implementations. Encapsulation. Encapsulation is one of the fundamental concepts in object-oriented programming, OOP. It describes the idea of wrapping data and the methods that work on data within one unit. This puts restrictions on accessing variables and methods directly and can prevent the accidental modification of data. To achieve encapsulation in Python, we can use private attributes, using underscores, and provide public methods to access and modify these attributes. In the code, the car class has 2 private attributes, core, model, and year, which are intended to be inaccessible from outside the class. It provides 2 public methods, getModel and setModel, which allow you to safely access and modify the model attribute. When the instance myCar is created, the model and core year attributes are set. The getModel method is called to print the model of the car, and the setModel method is called to change the model. The new model is printed using getModel. Access modifiers: public, protected, private. In Python, access modifiers dictate the accessibility of the attributes and methods within a class. They are essential for encapsulation, allowing us to restrict access to class components. There are 3 types of access modifiers: public, protected, and private. Public members, public var, can be freely accessed from outside the class. Protected members, protected var, are intended to be accessed only from within the class and its subclasses, with a convention to not access directly from outside. Private members, private var, however, cannot be accessed directly from outside the class. They can only be accessed within the class, such as by a method like accessedPrivate. Trying to directly access a private variable, as in the commented part of the code, will raise an attribute error. Special methods, repr, etc. In Python, special methods are used to override or add default functionality that is not explicitly called by the programmer, but by Python itself. The score and repr methods are two of such special methods that are used for creating string representations of objects. Here, the vector class has two special methods defined, repr and score. The repr method is supposed to return an official string representation of an object, ideally one that can be used to recreate the object. The star method is meant to return a nice string representation of an object, which is readable and user-friendly. When we print the object v, the star method is called, resulting in a user-friendly format. When we call repr v, the call repr method is executed, showing a string that looks like the valid Python code to recreate the object. Class and static methods. In Python, within the context of a class, we have different types of methods: instance methods, class methods, and static methods. Instance methods take self as their first parameter and can access and modify object instance state. Class methods take CLS as their first parameter and can modify class state that applies across all instances of the class. Static methods do not take self or CLS as their first parameter. They're like regular functions, but belong to the class's namespace. In the provided code, myClassMethod is a class method decorated with @classMethod. It can be called on the class itself, not an instance, to modify or access class-level attributes. myStaticMethod is a static method decorated with @staticMethod. It behaves like a regular function, but is encapsulated within the class, usually because it has some logical connection with the class, but doesn't need to access the class or instance-specific data. Property function. The property function in Python is a built-in function that creates and returns a property attribute. Properties are used in OOP to provide an interface to instance variables through getter, setter, and deleter methods, effectively encapsulating data and allowing controlled access to private variables. In this code, we define a class circle with a private variable radius. The methods getRadius, setRadius, and delRadius are defined to get, set, and delete the value of radius, respectively. We use the property function to create a property attribute radius. This allows us to use circle.radius syntax to access the radius with controlled behavior. If we try to set the radius to a negative value, the setRadius method raises a value error. Deleting the radius is achieved via delRadius. The last argument to the property function is a docstring describing the property. Data hiding. Data hiding in Python is a fundamental principle that involves restricting access to certain details of a class from outside interference or misuse. This is primarily achieved through the use of private variables, which are defined by the convention of prefixing the variable name with double underscores, core. In the provided code, we define a class myClass with a private variable, hidden variable. This variable is not directly accessible from outside the class, protecting it from unintentional modifications. Access to this variable is provided through a method getHiddenVariable, which is a common practice to interact with private attributes. Attempting to access score hidden variable directly will result in an attribute error, since Python performs name mangling on private variables. Uncomment the last line to see the error caused by attempting to access the private variable. Iterators. In Python, iterators are objects that can be iterated over. They implement the iterator protocol, which consists of the methods iter and callNext. The iter method, which is called on the collection object, returns the iterator object itself. The next method is called on the iterator to fetch the next item. When there are no more items to return, this method raises a stop iteration exception. The code defines a class counterIterator that represents a simple iterator which counts from 1 to a specified limit. The goInit method initializes the iterator with a limit. The itergo method returns the iterator object itself. The next method increments the count and returns the next value until the limit is reached, beyond which it raises a stop iteration exception. The for loop at the bottom iterates over counterIterator, printing numbers from 1 to 5, demonstrating how the iterator works. Generators. Generators are a simple way of creating iterators in Python. They allow you to declare a function that behaves like an iterator, i.e., it can be used in a for loop. Generators are written like regular functions, but use the yield statement whenever they want to return data. Each time next is called on it, the generator resumes where it left off. It remembers all the data values and which statement was last executed. They are more memory efficient than other sequence objects like lists, especially when dealing with large datasets. The code defines a generator function simple generator that takes max value as an argument. Inside the function, a loop runs as long as n is less than max value. On each iteration, n is yielded, then incremented by 1. The generator pauses after the yield statement and resumes when next is called again. When using the generator in a for loop, it automatically iterates over the values, printing each one until n reaches 100, without creating a full list in memory. Closures. In Python, a closure is a function object that remembers values in enclosing scopes even if they are not present in memory. It is a record that stores a function together with an environment, a mapping associating each free variable of the function with the value or reference to which the name was bound when the closure was created. In the provided code, outer function takes an argument msg and defines a nested function inner function which prints the variable message set to the value of msg. The outer function returns inner function without executing it. When outer function is called with the argument hello world, it returns the inner function. Inner function is now a closure that contains the reference to the variable message. Thus, even after outer function has finished execution, when myfunc is called later, it still has access to message and can print hello world. This demonstrates the use of closures to maintain state between function calls. Decorator functions. Decorators are a powerful feature of Python that allow you to modify the behavior of functions or classes. They are essentially functions that wrap another function and can add functionality before and after the wrapped function runs, without changing its original implementation. The code defines a decorator function, myDecorator, that accepts a function func as its argument. The decorator has an inner function wrapper that prints a message before and after calling func. The @myDecorator syntax is syntactic sugar for applying the decorator to the sayHello function. When sayHello is executed, wrapper is called, resulting in the additional messages being printed along with the original hello from sayHello. Context managers. In Python, context managers are a way of allocating and releasing some sort of resource exactly where you need it. The most common way to implement a context manager is using the with statement. It helps you manage resources efficiently by ensuring that setup and cleanup actions are always taken in a paired manner, even if an error occurs within the block. The with statement is used to create a context where open function is called to open a file named example.txt in write mode. The open function returns a context manager that ensures the file is closed after the block of code inside the with statement is executed. Even if an error occurs while writing to the file, the with block guarantees that the file is closed properly. Magic methods. Magic methods in Python are special methods that begin and end with double underscores, also known as dunder methods. e.g. init, add. They are not explicitly called, but rather invoked internally by Python when certain operations on objects are performed. For example, adding two objects with the plus operator automatically invokes the add method of those objects. In this code, we define a class circle that has an init method to initialize its radius, a star method to represent the circle object as a string, and an add method that lets us use the plus operator to add two circles together. The add method creates and returns a new circle instance, with the radius being the sum of the two circles' radii. When we create two circle instances and use the plus operator on them, the add method is called, and the result is a new circle instance that we print out. Descriptors. Descriptors are a low-level mechanism for implementing attributes with custom behavior. They are created by defining a class with at least one of the following methods: get, set, or delete, which are part of the descriptor protocol. Descriptors allow for the control over access, modification, and deletion of attributes. In the provided code, Celsius is a descriptor class because it defines get and set methods. The temperature class then creates a class attribute Celsius, which is an instance of Celsius. When we assign temp.celsius equals 30, it calls the scoreSet method of the descriptor, and when we print temp.celsius, it calls the get method. The descriptor handles the accessing and setting of the Celsius attribute, allowing for additional logic and control within those methods. Metaclasses. In Python, metaclasses are the classes of classes, meaning they define the behavior of classes themselves. They are a deep concept often not needed in everyday coding, but understanding them can give you a deeper insight into how Python works. In the given code, meta is defined as a metaclass, inheriting from type, with an overridden new method, which is called when a new class is created. Upon creating my class, we specify that meta should be its metaclass with metaclass equals meta. When my class is defined, the new method of meta is invoked, which prints the name of the class being created, my class. Sys. The sys module in Python is used to interact with the interpreter. It provides access to variables and functions that have a strong interaction with the Python interpreter. Common uses include reading command line arguments, fetching the Python version, and exiting the program. In the provided code, we import the sys module and then perform three common operations. First, we fetch the command line arguments passed to the script sys.argv, which includes the script name as the first element. Then, we print the version of Python currently running. Finally, we call sys.exit to terminate the program. Normally, you would use sys.exit with some condition or in an exception handler. OS. The OS module in Python provides a way of using operating system-dependent functionality. You can interact with the underlying operating system in many different ways, like navigating the file system, reading and writing files, and accessing system information. The code starts by importing the OS module, which is necessary to access its functions. Then, it retrieves the current working directory using os.getcwd, and lists all files and directories in the current directory using os.listdir. Next, it creates a new directory called new directory with os.kdir, renames it to rename directory with os.rename, and finally removes rename directory with os.rmdir. It covers basic file system operations provided by the OS module. JSON. The JSON module in Python's standard library allows you to work with JSON, JavaScript Object Notation data. JSON is a popular format for transferring data between a server and a web application. Python's JSON library provides an easy way to encode and decode JSON data. The code snippet begins by importing the JSON module. We define a Python dictionary named person with some data. We use json.dumps to convert the person dictionary into a JSON-formatted string, which we store in data.json. Then, we convert this JSON string back into a Python dictionary using json.loads. Dumps is short for dump string, whereas loads stands for load string. Datetime. The datetime module in Python's standard library provides classes for manipulating dates and times. These classes can help you perform operations such as calculating a future date, finding the difference between two dates, or simply displaying the current date and time. In the provided snippet, we import the datetime class from the datetime module. We then call the now method to get the current local date and time, which we store in a variable called now. Finally, we print the current date and time in a formatted string. Collections. The counter tool from the collections module is a specialized dictionary used to count objects. It is an unordered collection where elements are stored as dictionary keys and their counts as dictionary values. The code snippet imports counter from the collections module and creates a counter object for the string abracadabra, counting the occurrences of each character. It then retrieves the count of A's and updates the counter with additional A's and B's. Finally, it prints the updated counts showing the object frequency mapping. Functools. The Functools module offers higher-order functions that act on or return other functions. One key function of this module is partial, which is used to fix some number of arguments of a function, resulting in a new function with fewer arguments. In this code, partial is used to create a new function square that always raises a number to the power of 2. Square 10 calls the original power function with base set to 10 and exponent set to 2, resulting in 100. Itertools. The itertools.count function returns an iterator that produces consecutive integers indefinitely unless you provide a start and a step. The code imports count from the itertools module. It then creates an infinite iterator starting at 10, incrementing by 2 each time. A for loop is utilized to print the values. The loop breaks when the value exceeds 20 to prevent an infinite loop. Logging. In Python, the logging module provides a flexible framework for emitting log messages from Python programs. It is broadly used for tracking events that happen when some software runs. Logging can provide a traceable record of when, where, and why a certain piece of code was executed, which can be a crucial tool for debugging and system monitoring. The code above imports the logging module and configures it with a basic configuration setting, the log level, to info. This means that only log messages with a severity level of info or higher will be emitted. Messages with a lower severity, like debug, won't appear. The logging levels are debug, info, warning, error, and critical, with warning being the default if not set. The code then shows how to produce log messages at different severity levels. Typically, info messages are used for general output of programs, warning for minor issues, error for serious problems, and critical for very serious errors. Random. The random module in Python is used for generating pseudo-random numbers with various functions. It provides a suite of functions that can produce random numbers from different distributions, pick random elements from a sequence, shuffle sequences, and more. The random module does not require a piece of code to explain the preamble, since it is about its general purpose in Python. If we need to illustrate its use, we would typically import the module and use one of its functions, such as random.randint 099, to obtain a random integer between 0 and 99. Unit test. The unit test module is a built-in Python module that allows you to write test cases to check your code for correctness. Writing tests is a fundamental aspect of software development, ensuring that your functions work as expected. The code defines a test case test_sum that inherits from unittest.testCase. The test case includes a single test method, test_sum, that checks if the built-in Python function sum correctly calculates the sum of the numbers in a list. Unittest.main is called when running the script to execute the tests defined in the test_sum class. Reading and writing CSV files. CSV, comma-separated values files, are simple text files for storing tabular data. Python provides a built-in module called CSV that allows you to easily read from and write to CSV files. Here we'll focus on reading a CSV file using this module. In the provided code snippet, we import the CSV module and open a CSV file named example.csv in read mode. With the file opened, we instantiate a CSV reader object that can iterate over each line in the CSV file. We read the header with next CSV reader, which is typically the first line in a CSV file containing column names. Then we loop through each subsequent row in the file and print it. This code helps you understand how to access the data in a CSV file row by row in Python. Reading and writing JSON data. JSON, or JavaScript Object Notation, is a lightweight data interchange format. Python's built-in JSON module can be used to read JSON data from a file or a string and convert it into a Python object, as well as to take a Python object and convert it to a JSON string that can be written to a file. This is especially useful when working with APIs or storing and transmitting structured data. In this code snippet, we start by importing the JSON module. We create a dictionary named myData that we wish to export to a JSON file. We then open a file named data.json in write mode, W, and use json.dump to write the dictionary to the file in JSON format. When reading JSON data, we open data.json in read mode, R. The json.load function reads the file and converts the JSON data back into a Python object, in this case a dictionary, which we can then work with. The data is printed, showing the successful read operation. Handling XML with Elementary. Elementary is a Python library that's used for parsing and creating XML data. XML, Extensible Markup Language, is a markup language that defines a set of rules for encoding documents in a format that is both human-readable and machine-readable. The XML handling capabilities provided by Elementary allow you to navigate, search, modify, and create XML documents with ease. In the provided code snippet, we first import the Elementary module as ET. We create a multi-line string, XML string, that represents an XML document containing a list of books with their titles and authors. We parse this XML string using et.fromString and get the root element of the XML structure. Using a for loop, we iterate through each book element under the root, find the title and author child elements, and then print out their text content. This illustrates the basic parsing and navigation capabilities of the Elementary library. Working with SQL databases. In order to work with SQL databases in Python, the SQLite 3 module is utilized for interacting with a SQLite database. SQLite is a C library that provides a lightweight, disk-based database that doesn't require a separate server process. Here's how to establish a connection. The code imports the SQLite 3 module and then creates a connection object by calling the SQLite3.connect function. If mydatabase.db doesn't exist, it will be created. A cursor object is then created from the connection. The cursor object is used to execute SQL queries. Using pandas for data analysis. Pandas is a high-level data manipulation tool built on top of the Python programming language. It offers data structures and operations for manipulating numerical tables and time series. Here's how to start using pandas. This code first imports the pandas library and assigns it the common alias PD. Then, we create a simple dictionary with data and convert it to a data frame, which is a core data structure in pandas, resembling a table. Finally, we display the content of the data frame. Using the PDB debugger. The PDB module is the Python debugger, which allows you to step through your code, examine variables, and evaluate expressions. It's an essential tool for debugging Python programs. To use PDB, you typically insert a breakpoint in your code, which pauses execution and gives you the chance to inspect the program state. In this code, pdb.setTrace is called to set a breakpoint. When the program executes, it will pause before executing the next line. At this point, you can use commands such as C to continue execution, N to step to the next line, L to view where you are in the code, P to print a variable, e.g. PA, Q to quit the debugger, and H for help. The calculate_sum function is a simple example. When the breakpoint is hit, you'll be able to inspect the values of A and B and step through the addition and return statement. Writing unit tests with unit test. In Python, the unit test module is used to write unit tests. A unit test checks the correctness of a small unit of code, typically a function or a method. The unit test framework provides features to assert conditions, set up test environments, and more. The module supports test automation, sharing of setup and shutdown code, aggregation of tests into collections, and independence of the tests from the reporting framework. This code demonstrates how to structure a basic unit test using Python's built-in unit test module. A simple function called add is defined, which is intended to add two values. We then create a subclass of unittest.testCase, which is a built-in class that defines the framework for the test case. Inside this subclass, we define a method test_add that uses assert_equal to verify that the add function returns the correct result when it's called with different arguments. Finally, the last block checks if the script is run directly, and if so, calls unittest.main to run the tests. Test cases and test suites. In testing, a test case is a set of conditions or variables under which a tester will determine whether an application, software system, or one of its features is working as it was originally established for it to do. Here we're importing the unit test module, which is Python's standard library for writing and running tests. We use this module to create individual test cases by subclassing unittest.testCase. Running tests. Running tests is an essential activity to ensure that your code behaves as expected. Python's standard library includes the unit test module, which contains tools for constructing and running tests. This code snippet defines a test case by creating a subclass of unittest.testCase called simpleTest. Within this subclass, we define a method, testAddition, that tests whether the sum function correctly adds the numbers in a list. To verify this, we use the assert_equal method provided by unittest.testCase to assert that the sum of 1, 2, 3 should equal 6. At the bottom, the ifName=main block is used to run the tests when the script is executed directly. The unittest.main function provides a command line interface to the test script. Skip tests and expected failures. In testing, certain scenarios may require that some tests be skipped under specific conditions, like limited resources, missing dependencies, or a test environment issue. Python's unit test framework provides a mechanism to skip tests using decorators, mocking objects. In testing, mocking is a technique used to simulate the behavior of real objects. This is useful when actual objects are impractical or impossible to incorporate into tests, such as when dealing with network resources, databases, or other external services. The unittest.mock module in Python allows you to replicate and customize these objects' behavior within your tests. In the code sample provided, we start by importing magicmock from unittest.mock. We have a production class with a method that we want to mock. We create an instance of magicmock and assign it to the method of an instance of the production class. This replacement allows us to simulate any call made to method. We then call the method with some arguments and assert it was called with those exact arguments using the assert_called_with method on the mock object. Creating virtual environments with venv. The venv module in Python is used to create isolated virtual environments. Each environment has its own installation directories and doesn't share libraries with other environments. This is useful when you want to work on different projects with differing dependencies. First, the command python-m venv myscoreEnvironment is executed to create a new virtual environment called myEnvironment. The venv module is invoked with the -m flag, directing Python to run the supplied module as a script. The following source myEnvironment/bin activate command is used to activate the virtual environment for Unix-based systems, which changes the shell's environment to use the binaries and libraries from myEnvironment instead of the global Python installation. On Windows, the equivalent activation command is myEnvironment scripts activate. Managing dependencies with pip. Pip is a package installer for Python. It allows you to install and manage additional libraries and dependencies that are not distributed as part of the standard library. Managing dependencies is crucial for ensuring that your Python projects run consistently across different environments and systems. The first command, pip install requests, installs the requests library. Pip list shows a list of installed packages. Pip freeze outputs all installed packages in a requirements format. Requirements.txt saves this output to a file. The last command, pip install dar requirements.txt, installs packages from the requirements.txt file, ensuring you have all necessary dependencies. Using requirement files. Requirement files are text files that contain a list of items to be installed using pip install. This concept is crucial for managing packages for a specific project, ensuring that all dependencies are listed and version controlled so anyone with the file can recreate the identical environment. The command pip freeze outputs a list of all installed packages in the current environment, along with their versions. Operator in shell tells the system to redirect that list into a file named requirements.txt. This file can then be committed into version control and later used to install the exact same set of packages using pip install-r requirements.txt. Package versioning and distribution. Package versioning is essential for managing dependencies of Python projects. Each version of a package can introduce new features, fixes, or even breaking changes. Semantic versioning, SEMVer, is the most common scheme used, comprising 3 parts: major, minor, and patch, e.g. 1.0.0. In semantic versioning, the major number increases with incompatible API changes, the minor number with added functionality in a backwards compatible manner, and the patch number with backwards compatible bug fixes. By pinning specific package versions in a project's requirements file, developers ensure consistency and prevent unexpected changes from affecting their projects. Using virtualenv and pyenv. Virtualenv is a tool used to create isolated Python environments. It allows you to manage separate package installations for different projects, avoiding conflicts between package versions or requirements. First, we install virtualenv using pip. Next, we create a new virtual environment named myprojectenv using the virtualenv command. Finally, we activate the environment. On Windows, the activation command is different. myprojectenv scripts activate. PEP 8 Style Guide for Python Code. PEP 8 is a document that provides guidelines and best practices on how to write Python code. It was written by Guido van Rossum, Barry Warsaw, and Nick Coughlin in 2001 to improve the readability and consistency of Python code. PEP stands for Python Enhancement Proposal, and PEP 8 has become the standard style guide for Python code. This example follows PEP 8 guidelines. Modules are imported at the top of the file. 2 blank lines precede the main function definition to visually separate it from imports. The main function name is descriptive and lowercase. Indentation uses 4 spaces per level, and the main script execution check is included at the bottom. Following PEP 8 results in more readable, maintainable, and community-standardized code. Writing readable code. Readable code is not just about making it understandable for others, but also for your future self. It involves writing code in such a way that is clean, simple, and easy to understand. This includes following naming conventions, adding comments where necessary, and structuring the code for legibility. This function is an example of readable code. The function name, calculateArea, clearly indicates its purpose, and the variables base and height are straightforward. The comment above the return statement explains what the code does, which is calculating the area of a triangle using the standard formula. The mathematical operation in the return statement is simple and does not include any unnecessary complexity, making it easy to understand at a glance. Code optimization. Code optimization is the process of modifying a software system to make some part of it work more efficiently or use fewer resources. In Python, this often means improving the speed at which a program runs or reducing its memory consumption. In the code example, we define a function to calculate the sum of squares up to a given number n. Instead of building a list of squares and then summing it, which would take more memory, we use a generator expression, xtor x for x in 1 n plus 1. This is more memory efficient, as generator expressions lazily yield items one by one, instead of storing the whole list in memory before summing the elements. This is a simple form of memory optimization. Documentation using Sphinx. Sphinx is a tool that makes it easy to create intelligent and beautiful documentation for Python projects, or other programming languages, based on restructured text and Python doc strings. It's used by many large Python projects. To use Sphinx, you first need to install it using pip. After installation, Sphinx Quick Start is the command that sets up a basic documentation structure. It creates a source directory with conf.py, configuration file, index.rst, master document, and makefiles for easy building. Customize conf.py to set the project details, and create .rst files to write your documentation in restructured text, or use Autodoc to include doc strings from the code. Version control with Git. Version control systems are essential tools for developers, enabling them to track changes, collaborate, and manage code. Git is a widely used version control system. It helps manage project files and keep the history of changes. The git init command initializes a new Git repository locally. it creates a hidden directory called .git that houses all of the necessary metadata for the new repository. This command only needs to be run once per project to start tracking changes.